Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Let us embark on an exploration of the remarkable achievement of 1973, the year Michael Atiyah and Isadore Singer presented their seminal work, the Index Theorem. This theorem, a cornerstone of modern mathematics, transcends mere mathematical curiosity, reaching into the realms of physics and profoundly shaping our understanding of the intellectual tapestry woven before the 1973 Index Theorem possessed threads of diverse origin. The quest to understand the properties of elliptic operators, a class of differential operators arising in numerous areas of physics and geometry, formed a central theme. These operators, characterized by their smoothness and well-defined behavior, presented a challenge to understand the relationship between the analytical properties of their solutions and the topological characteristics of the spaces on which they acted. The initial impulse to address this intricate linkage traces back to the early 20th century. The development of spectral theory, particularly the work of David Hilbert and others on the properties of linear operators on Hilbert spaces, provided vital tools. The study of Fredholm operators, operators with finite dimensional kernels and cokenals, by mathematicians like Fritz Noether and I.M. Gelfand, provided the initial groundwork necessary for understanding the index. The index of a Fredholm operator, defined as the difference between the dimensions of its kernel and cokenal, became a central object of investigation. This number, an integer, encoded information about the operator's failure to be inverse. The Atiyah-Singer index theorem's formulation represents a profound synthesis of several fields. This theorem provided a breathtaking connection between analysis, particularly the theory of elliptic operators, and topology, the study of geometric properties invariant under continuous deformations. At its heart, the theorem connected the analytical index of an elliptic operator, a concept rooted in the analysis of the operator's kernel and cokenal, with a topological invariant derived from the geometry of the underlying space. The precise statement is, in its core, deceptively simple. The index of a Dirac operator on a compact manifold is equal to the integral over the manifold of a certain characteristic class, also known as the genus. Related to the manifold's curvature, the Dirac operator, a fundamental object in mathematical physics, acts on sections of a spinor bundle over the manifold. The proof of this theorem, a monumental achievement in its own right, involved several innovative techniques. They utilized cobordism theory, a powerful tool for classifying manifolds, in conjunction with sophisticated analytical arguments. The theorem was proved by constructing a family index, a generalization of the index to families of operators parametrized by space. By analyzing the properties of this family index, Atiyah and Singer could relate the analytical index to a topological invariant. This process proved to be intricate, demanding the development of new tools and the refinement of existing mathematical techniques. It was a testament to their combined brilliance, seamlessly integrating algebraic topology, differential geometry, and functional analysis. The immediate impact of the index theorem was nothing short of transformative. Its initial application lay in the elegant derivation of known and, importantly, the discovery of new topological results. It provided a unified perspective on problems in diverse areas of mathematics, including the study of the Riemann-Roch theorem, the Hirzebruch signature theorem, and the Gauss-Bonnet theorem. The theorem offered a powerful framework for the study of elliptic operators on manifolds, leading to the development of new tools and techniques. It also spurred a wave of generalizations and refinements, extending its applicability to different types of operators and more general space. The influence of the index theorem on subsequent mathematical and physical developments has been vast and multifaceted. It served as a catalyst for the development of non-commutative geometry, a generalization of geometry that allows for the study of spaces whose coordinates do necessarily commute. Alain Connes, in his pioneering work, utilized the index theorem as a guide in developing the fundamental principles of this fascinating new field. Furthermore, the index theorem played a critical role in the advancement of string theory, a physical theory that seeks to unify all fundamental forces of nature. It provided a mathematical framework for understanding the anomalies and symmetries in string theory, enriching the physical understanding of the universe. The theorem's influence is also apparent in condensed matter physics, where it finds application in the study of topological insulators, materials with intriguing and exotic properties. These materials feature a bulk that behaves as an insulator, with conducting surface states whose behavior adheres to topological principles, which in turn lead to the application of the index theorem. The index theorem did not escape criticism. It has spurred much debate and discussion about its mathematical and physical interpretations. Some mathematicians and physicists critiqued the theorem's reliance on advanced mathematical machinery, questioning its accessibility to researchers in other fields. The proof's complexity required an extensive preparation in multiple areas of mathematics and required an understanding of advanced material. Such difficulties resulted in a relatively slow adoption rate within other areas of mathematics and physics. Initially, moreover, some questioned the generality of certain applications of the theorem, particularly in contexts where the assumptions of the theorem were not fully satisfied. Despite these criticisms, the index theorem's enduring value has remained steadfast. The formulation of the index theorem owes an immense debt to certain individuals and prior works. The works of mathematicians like Georges de Rham and Werner Gysin provided vital initial intuitions connecting analysis and topology. De Rham's theorem, for example, which relates the de Rham cohomology of a manifold to its singular homology, provided a crucial connection between differential forms and topological invariants. The index theory of Fredholm operators and the work of singular integral operators, building on earlier work by mathematicians such as Noether and Fredholm, furnished the foundational tools necessary for the theorem's formulation. Likewise, the work of Herzebrach on the signature theorem established a crucial precedent by connecting analytic invariants with topological ones in a specific context. The work of Gelfand and others, studying the index of elliptic operators on compact manifolds, was also fundamental in setting the stage for the Atiyah-Singer theorem. Their contributions shaped the intellectual landscape from which the index theorem emerged. The impact of the Atiyah-Singer index theorem on subsequent work has been both profound and far-reaching. The theorem inspired a generation of mathematicians and physicists, leading to the development of new areas of research and significant advances in existing fields. The theorem's influence is reflected in the work of many distinguished researchers. For instance, the development of K-theory, a sophisticated branch of topology that classifies vector bundles, finds its roots in the index theorem. The theorem provided a driving force in the development of geometric quantization, a mathematical framework that connects classical and quantum mechanics. Edward Witten, in his work on the relationship between topology and quantum field theory, demonstrated the deep connections between the index theorem and physical phenomena. The theorem also significantly influenced the development of the theory of gauge fields, which describes fundamental forces such as electromagnetism and the weak nuclear force. The theorem's influence can be seen in the work of many more physicists. The Atiyah-Singer index theorem has left an indelible mark on the landscape of modern science. In conclusion, the 1973 Atiyah-Singer index theorem represents a pinnacle of mathematical achievement, a testament to the power of human intellect. It unified seemingly disparate areas of mathematics and profoundly shaped our understanding of the natural world. The theorem's enduring legacy lies not only in its profound results, but also in its transformative impact on subsequent research and its continued relevance in contemporary physics and mathematics. It stands as a beacon of intellectual brilliance, illuminating the path for future generations of scientists and mathematicians. The index theorem serves as a powerful reminder that the pursuit of knowledge, when guided by insight and imagination, can yield not only profound insights, but also transform our very comprehension of the cosmos.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.